So we have a number of speakers, and so this is going to be action-packed and fast-moving. I'm going to spend very little time talking. I'm going to make very brief introductions, and then I'm going to ask these folks to come up one at a time. And you be prepared and be focused, and before you know it, you will be a lot smarter about this subject than you were an hour from now. Our first speaker is Bob Hansen, retired professor from the University of Michigan, and many other things. He said, don't read my whole bio out here, but Bob has been an integral part and an absolutely critical member of FEMA's NEHRP team for many, many years, and has a list of accomplishments that is very long and very distinguished. And with that, Bob.
Thank you, Ed. I got a good introduction today, both from Keith Porter and from Ed and from Jack Hayes. What I'm talking about is a technique, a tool that FEMA's been developing over the last almost 14 years now for performance-based design. And what you're looking for is better performance of the building, not just looking at life safety, but looking at really improved performance of the building. And so I'm going to go through some of these very quickly. The ATC FEMA team is led by Mike Mahoney and John Heinz and Asha. The project management committee is led by Ron Hamburger, and you can read the names faster than I can read the names. Bill Holmes is chairman of the steering committee. He's sitting up here with us. And there are 3 performance groups in the current project. The performance project team is led by John Gilligerton, the stakeholders by Laura Samant, and the products team by John Hooper. Those of you in the earthquake community, the engineering side, will recognize all of these names. It's a 2-phase program. The first phase started in 2003 and completed in about 2012, and that is the assessment part of the process. The second phase is what we're working on now, and that's the development of design guidelines and stakeholder guides to implement a performance design procedure. The assessment process is a probabilistic approach. It's not deterministic, and it looks at casualties being injuries as well as death, repair costs, repair times, and it's also in the next version including environmental impacts such as carbon depletion costs. So it's a very broad-based approach. It's conditioned on 3 things: the earthquake intensity, earthquake scenario, or all possible earthquakes. So you have your choice. You can either pick a code level earthquake design or a specific earthquake for your location, or you can consider the probabilistic of all earthquakes for that site, similar to what the uniform hazard codes that Nico Luco talked about today. The building assessment part of it starts with a ground motion. And again, you have your choice of trying to do either of those 3 ways. The ground motion goes into your structural model. You look at the damages caused by the response of that structure, and then evaluate how much time it's going to take to repair the structure, what the casualties are, and what the costs of repair are. And so what we start with is a building performance model. Now the model includes the structure, the non-structural elements, the contents, and everything that is in that building. Now, when putting this model together, there are certain things that are not what we would call hazardous earthquake things. For example, toilets in a toilet room very seldom get damaged in an earthquake, and so therefore putting that into the model probably is wasting time and effort, because the losses due to a cracked toilet is not likely to happen, first of all, and the cost is relatively small. So we analyze the building response. We determine what the response is, and we have essentially two choices. We can do a nonlinear time history response, or we can take and do a simple estimate of what this response is. Now, the responses that we're looking for are floor accelerations, interstory drifts, and velocities. Based on those input parameters, we then can determine what the response is going to be. And again, as I said when I started, it's a probabilistic, so we have a mean value of these characteristics, but then we also have a dispersion or a probabilistic range on that. Now this gets to be pretty small for me to see up here. I hope you can see it better out there. But we do the calculation of the response, and what we do is spin the wheel hundreds to thousands of times, in which you are varying the demands, you're varying the damage, and you're varying the consequences. So you have all these three different variables operating at the same time to end up with a probabilistic distribution. Then you look at the results, and here I just plotted the results in a graphic type of form, where each of these boxes represents the damage, in this particular case, damage for the structure, for the non-structural, for the glass, for the ceilings, for the interior partitions, or for any other particular element that you're looking at for damage and the consequences. In this particular case, as illustration, for this magnitude 7.2 earthquake on the Hayward Fault, this building was very close to the Hayward Fault. The probability of an unsafe placard, which is a red tag if you want to think of it that way, was 10%. The median repair cost was $820,000, and the probabilistic maximum loss, which is what MPL is, what a lot of people do, is $1.5 million, and the repair time is about 8 weeks. Now, you can look at it that way as one example, but what this process allows you to do is to modify the structure, and in this case, we illustrate 3 different structures. The basic structure that you would normally design just to the minimum of code design. You increase it to a higher performance level, like Keith Porter suggested earlier, and you get a better performance. And then if you put in base isolation or dampers, so you actually control the displacements and the accelerations, you get much better performance. And so you can see from these various curves, which one, this one here, oops, I gotta go back one, I guess. So. Your normal one, this is just for repair time, but you can do the same thing for cost and for casualties. Your repair time goes up for the basic design. It comes down substantially for your enhanced performance design, and even smaller for you have special construction details. Now, as Keith mentioned before, the difference in cost between these 3 different models is not very significant in many cases. And so you can end up with a much better performing system with relatively little investment in initial construction. And so, as we indicated, 2012, we finished this assessment process. And so FEMA P58 is a tool that is now available to allow the assessment of the probable performance of individual buildings. P58 has been adopted in practice by several programs. SP3, which is produced by one company, READY is by another. These have been done with some modification. They don't use exactly what P58 is. They do some little adjustments to it. And this tool is also established and provided by FEMA in a calculation tool called PACT. PACT is available in its current form with a P58, but I recommend that you don't use it at this stage. I would hold off until July, when packed will be updated with the most recent information, and this CD will be available for you to take and run it yourself, or you can contact some of these other agencies or other companies to have it run for you. So in summary, the current work is developing a methodology for enhancing the current PACT program and developing practical tools for the design. Now, in phase 2, remember, we're trying to use the design step that after you've done the design, then you do the assessment, and practical guidance for stakeholders and inclusion of environmental considerations. The current, what we're working actively on is assist decision makers in selecting performance objectives. Not all owners know what they want the building to do, and so they need guidance on deciding what they want to do. And not all design professionals have worked with performance-based design yet, and so we need to develop some guidance to help them do that. And one of the first major steps we're working on right now is to calibrate existing code-designed buildings in terms of what their performance really is, so we can try to judge whether our existing codes are achieving what we believe they are achieving. And then finally, to provide design guidance for building owners and building engineers. Thank you.
Thanks very much, Bob. Very good remarks and right on time. Excellent. So our next speaker is Mike Tong. And I happen to know something about Mike Tong because we've worked together for the last several years. Mike is a physical scientist at of the NEC program at FEMA and has been there since 2007? My gosh, where does the time go? He serves as a project officer and provides oversight for the development of various NEC technical guidance codes and standard resource documents and tools, including the recently released 2015 NEC recommended provisions. I assume many of us know what that is. Prior to working for FEMA, he was a senior research scientist at the Multidisciplinary Center for Earthquake Engineering Research, MCER, in Buffalo, New York. And Mike, all yours.
Thanks, Ed, for the introduction. So my presentation is titled NEC Recommended Seismic Provisions for New Buildings and Other Structures, Past, Present, and Future. The story of the NEC provisions can be traced back, actually, to an earthquake occurred not too far from here 45 years ago. It's the San Fernando earthquake. That earthquake of magnitude 6.6 caused 64 fatalities and collapsed a number of the buildings. It is this earthquake that triggered quite the concerns of the building code used then. Some of you may already recognize the pictures shown on this slide. On the top there, the two pictures show the Oliver View Hospital that was collapsed in this earthquake. And the bottom one is the VA hospital, also collapsed in this earthquake and cost over 40 people's lives. So after this earthquake and following the recommendations of the Seismic Research Committee and the Design Practicing Committee, the National Science Foundation funded Applied Technology Council develop a report entitled Tentative Provisions for Developing Seismic Regulation for Buildings, and that is the predecessor of the NEC provisions. And since then, 1977, the Congress authorized the NEC Act, which enabled the NEC agencies to support and expand the ATC 306 into a resource document, that is the NEC provisions. 45 years has passed since the San Fernando earthquake, and here's a timeline that shows the history of the NEC provisions as well as its evolution. The first edition of the NEC provisions was developed at Building Seismic Safety Council, BSSC, and published by FEMA in 1985. Since then, every 3 years, the NER provisions was updated into a new edition until 2003. Then the update cycle was changed into 5 or 6 years. So last year, FEMA published the 2015 NER provisions, also known as the FEMA P1050, and that is the ninth edition. Over the NER provisions of history, several of the major earthquakes occurred in the U.S. and around the world, provided valuable lesson learned information for this resource document. So today, our building codes already taking measures to safeguard our new buildings from the damage and issues found in these earthquakes, as listed here in the red. As a major code resource document, NER provisions played some very critical roles in the past for our national model building codes. Prior to 2000, Prior to 2000, the NER provisions mainly served as a code language resource document for the 3 national model building codes. But since then, in the 2000, the 3 national model building code merged into international building code. And in the inaugural edition, the IBC 2000 used the 97 NER provisions directly as the seismic requirements. Then in 2006, how do I get back? Okay, in 2006, IBC had started to directly reference the ASC 705, which is based on the 2003 NER provisions. And since then, the IBC continues to directly adopt by reference of the ASC 7, the most current edition until now. So, as the ASC 7 starts to be accepted widely as the national design standards for seismic, so the NER provisions transition its role of code language maintenance to the ASC 7. And in the 2009 NER provisions, it starts to adopt the ASC 705, and then based on the adopted edition of the ASC 7, develop additional new additions and changes, and that changes gets used by the ASC 710, which is further adopted by IBC 12 and 15. Then in 2015 NER provisions, it adopted ASC 710, then made additional new changes, and those changes were further used by ASC 716, and that is expected to be released this year, and also expected to be adopted by IBC 18. Looks like this relationship will continue in the foreseeable future. So today, the NER provisions serve a key role for the NEHRB. It is a new knowledge-based resource document. It serves as a venue to evaluate and translate USGS hazard map, FEMA and NIST, problem-focused studies, and fundamental research results, as well as lessons learned from the earthquakes for improving standards and codes. To serve this new role, the NER provisions has also been reformatted. The current NER provisions has 3 parts. Part 1 contains the changes, the modifications of the adopted ASC 7, and Part 2 is a complete commentary of the NER provisions. Then Part 3 collects the resource papers, mostly the new or emerging design methods and new concepts. The Provisions Update Committee, PUC, also reformed the structure to develop the change proposals. In the 2015 NER Provisions Update cycle, the Provisions Update Committee formed 11 issue teams and 3 work groups to develop targeted and specific issue-related change proposals. And these change proposals were evaluated and balloted through the PUC, then the BSSE member organizations. The PUC also worked with ASC 7 Seismic Subcommittee and the BSSC's Code Resource Support Committee for any of the standards or code issues that will need the PUC input. So the contents of the 2015 year provisions, there were 43 technical change proposals eventually passed the BSSC consensus and accepted into 2015 year provisions. These change proposals cover a wide range of the topics. Listed here are some of the major change topic areas. Each one of them can be presented in 30 minutes or an hour for the details. So in the interest of the time, I will skip talking about the details here. But I would like to encourage you to follow the BSSC's webinar series, and that will cover each of the topics on the 2015 year provisions. Going forward, we just formed the 2020 year provisions updated committee. Recently, in March this year, a BSSC held a colloquium and the first PUC meeting in that the issues recommended by the previous PUC were evaluated for developing new issue teams for the new cycle. One of the areas that this cycle of the PUC is going to be focused on is to address the seismic ground motion and its related design issues. This work is going to be a collaboration with Project 17, which is another committee jointly supported by FEMA and USGS at BSSC, and Nicole is going to talk about that after my presentation. So I'd like to finish by showing the membership of the 2020 NER provisions. There are 23 subject matter experts serving on the committee, as well as the 4 NEHRB agency liaisons. The subject matter experts are all volunteering, so I would really like to thank them and the BSSC for their strong support of this resource developing this resource document. So with that, and then I would like to look forward to your input and also continue to work to make this national code resource document to continue to be successful to support our building codes and standards. With that, thank you.
Thank you very much, Mike. As you probably already noticed, we're going to save questions only because we have so many speakers till we get to the end, and we will hopefully have a little bit of time to take a couple of questions at the end, but I want to make sure we get through the material. The next speaker is Dr. Nico Luco, and you have heard him speak already today, but just as a reminder, Dr. Nico Luco is a research structural engineer with the U.S. Geological Survey in Golden, Colorado. There he leads seismic design map tasks on the National Seismic Hazard Mapping Project and is the co-project chief of the Engineering Risk Assessment Project. Prior to joining USGS, he was a senior analysis engineer with the catastrophic loss modeling company AIR Worldwide. Please welcome Dr. Luco.
All right. Thank you. So a couple slides are going to look familiar, so we can go more quickly through those. So just to reiterate that the ground motion maps in building codes, like you see in the top center there, they're based on both the USGS National Seismic Hazard Model and the site-specific ground motion procedures that are in Chapter 21 of the NEHRB recommended provisions that Mike Tong just described. And again, it's the BSSC Provisions Update Committee, appropriately named, that bridges these things or connects these things together to get the maps that ultimately end up in the International Building Code. All right, so the beginning of this connection really started with Project 97 back in 1997, established the procedures for really basing the building code ground motion maps directly on the National Seismic Hazard Model. And then in Project 07 in 2007, 10 years later, that was reassessed, and we ended up with sort of the risk-targeted maps that are now in our building codes. So again, Project 17 will propose new ground motion maps for the 2020 NEC provisions that you heard Mike Tong describe, and which would ultimately feed into the 2024 International Building Code. All right, so that you'd seen before. The motivation really for Project 17 is something you can start reading now. So the design maps derived from the 2014 USGS hazard model. They were voted into the 2015 NEC provisions and ASC 716 and are on their way to the 2018 International Building Code. But along the way, there were several no votes. And this is an example of one of those no votes that I won't read to you, so I'm hoping you're reading. I'll only read the last line that really there was further discussion of overall seismic map directions and its impact on users that's needed because we've gone through enough cycles now to see some fluctuations. I'll give you an example of those in a moment. So this really motivated Project 17, and the first thing that was done was to form a Project 17 planning committee. A planning committee of about half practicing engineers that serve on building code committees like the PUC, and then several researchers mostly on the science side, some engineering like myself and Sanaz Rizayan from USGS as well as FEMA folks. Right, so this was just the planning committee. There's also a Project 17 execution committee that has some of the same folks, but it's a bit different list. Right. So that Project 17 planning committee, through discussions on its own and also some public webinars, identified 13 issues that were considered important for Project 17 to look at, again, feeding into the 2020 NEC provisions. However, faced with limited funding, Project 17 really had to prioritize and ended up focusing on 4 of these design map issues, which, and I mentioned this morning, but now I'll kind of give you a little bit more information on each of those 4 topics. All right, so starting with the first one, balancing changes / instability and precision with uncertainty in hazard modeling. So this was, again, one of the main motivations for Project 17 at all. So this is a couple lines that just show along the x-axis different editions of the International Building Code from 2000, 2006, 2012, and the upcoming 2018 International Building Code. And then the ground motion values, the building codes have a short period for shorter buildings, ground motion value, and a longer period for taller buildings, ground motion values. The shorter period values are the blue line on top, and this is for a location in the Santa Barbara area. And so it's a plot like this that drives engineers crazy. So looking at the yo-yo effect here, right? And a lot of times this gets interpreted as, well, we knew the answer in 2000, and then we just thought the answer was different in 2006, and we thought the answer was different again in 2012, and then we were back to in 2018 thinking the answer was what it was to begin with. But really what this misses is that there's a lot of uncertainty in getting at these ground motion values, and that's something that we need to keep in perspective when we look at a plot like this. So for Santa Barbara, here's an example of that Santa Barbara site. The blue distribution there is really showing the uncertainty about the 1 point that was shown on the previous plot. We're taking kind of a mean from that distribution, but there's uncertainty about that. So that's, the blue is showing the values that are being proposed for the 2018 IBC, just the mean value from that, but the uncertainty about it. And then the red shows you the value that was in the 2012 International Building Code. So it helps to give you some perspective on whether this change is quote unquote in the noise, or is it a more significant change? In this case for Santa Barbara, it looks like, the red value wasn't it is not, the red mean, that red bar there, isn't in the bulk of the new distribution that we have for ground motion. So this is probably telling you something that's a more significant change. So this is the kind of information that's going to be looked at very closely in Project 17 on this topic of balancing the changes with the uncertainty and the hazard. So the second topic is target risk of collapse. I showed this map too, the boring map that's 1% in 50-year collapse risk across the country. That's our target, and that's what we're setting our ground motion maps to deliver. But in California, we have these deterministically capped areas, and so we're allowing higher risk than the 1% in 50-year risk. And this has led some people to think about both deterministic capping, but also whether our 1% in 50-year target is the right one. It's based on analysis of structures, not a bunch of data of collapsed building, which fortunately we don't have. And so there's thought that it's a pessimistic number. If you kind of do some mental math, 1% in 50 years, it sounds kind of bad when you extrapolate out. So those numbers are something that are going to be looked at again in Project 17. Multi-period ground motion spectra is another topic for Project 17. So right now the building codes just use again, kind of a short period and a longer period ground motion acceleration value, and then they create that kind of bottom left spectrum just with a basic functional form. On the other hand, the USGS now for several years has provided ground motion information that would correspond to other spectral periods, other heights of buildings in loose terms. And now Project 17 is going to look into making use of that, but it's not a trivial task. You got to look at the implications throughout the code document. Similarly, the current maps in NEHR provisions or the IBC are for a reference soil condition, kind of the boundary between NEHR B and C. And then there are NEHR site factors that are shown in the bottom left here that take you to other, usually more common soil types for a particular site. On the other hand, USGS in the past has done calculations directly of hazard for different soil types, for different values of VS30, essentially stiffnesses of soils. And again, Project 17 wants to look at making use of that USGS hazard information more directly. And there is some potential for significant changes when you do make that shift from coefficients applied afterwards to results directly from hazard analysis. And then there's deterministic ground motion caps. This was a topic that was put on hold for a little bit because the thought was maybe there wouldn't be a need for this any longer if you change sort of risk-targeted approaches. But this is back in play. It started as really an effort to look at how that deterministic capping of otherwise probabilistic ground motion maps was done. The code tells you that you look at characteristic earthquakes on all known active faults within the region. Well, those familiar with USERF3, that Uniform California Earthquake Rupture Forecast, know that characteristic ruptures aren't really part of that model anymore. So there's that issue. And then there's also just the issue of still looking at deterministic versus probabilistic approaches to design. So that's the fourth topic. So just to summarize, and this is Project 17 is the collaboration between BSSE and that's what has funding from FEMA and the USGS. This is going to end up with new ground motion maps that ultimately would be proposed at least for the 2024 International Building Code, and before then the 2020 NEHR provisions. It was really motivated by those negative votes, so those negative votes were a good thing, as well as the fact that 10 years ago and 10 years before that, we really had a closer look at how we use hazard information in our ground motion mapping. And then this is just a recap of those four topics for Project 17. So with that, I'll close. Thanks again.
Thank you very much. Our next speaker is Mr. Bill Holmes. And Bill Holmes has been in the structural engineering and design and seismic design business for a little while. He started with Rutherford and Shakeen in 1965 and has been responsible for the structural design or seismic retrofit of a wide variety of buildings. He had a key role in the conceptual development of the NEHR guidelines and the update committee, and was responsible for the updates for the provisions for both the 1997 and 2000 editions for the new buildings. It says here in your little bio that you're actually retired now, but noticing how many times I've seen your name in the last few minutes, it seems that perhaps that retirement business isn't working out so well.
I'm real lousy at retirement, that's for sure.
Thank you.
Yeah, my wife tells me I'm terrible at retiring. This is another FEMA-funded ATC project. It's got several different names, but basically we're trying to come up with a pretty simple evaluation methodology for older concrete non-ductile buildings that have a high collapse potential. And I'm the technical director, and you can see the other committee members. ATC usually has about 5 people on these projects. Why is FEMA spending money on this building type? Well, older concrete buildings are known to collapse, certainly in other countries, maybe less so in the U.S., but there have been collapses, particularly in the San Fernando earthquake and the Northridge earthquake. And more significantly, the collapse can be a story wide or actually the whole building, so they can be very lethal collapses. This is another reason to show that. This was in the San Fernando earthquake, and that's a 2-story building. It appears to be a 1-story building. Miraculously, no one was killed because this was a part of a hospital, and all the patients were in their rooms on the 2nd floor. The 1st floor was all used for other purposes, so no one was hurt in that building. But this is the kind of thing that we're worried about, and it doesn't happen to a lot of buildings, but when it does happen, it's quite catastrophic. So EERI, you heard a lot about. It had another initiative starting maybe 10 years ago called the Concrete Coalition. And the Concrete Coalition was trying to take the decades-old concerns about these older concrete buildings that within the structural engineering community and try to actually do something about it, try to get some policy, make people aware of the problem and get some policies to start fixing some of these buildings. So it succeeded, and it kind of got FEMA's attention, and so FEMA decided to fund this development of this project that would somehow be able to identify what the Concrete Coalition called killer buildings. And whether that's 5 or 10% of all the older concrete buildings, it's unclear, but it's certainly not all of them. They're not like unreinforced masonry buildings where you can pass an ordinance and say fix them all because every one of them is liable to collapse. Older concrete buildings are not like that. So unfortunately, we have a very robust and sophisticated evaluation of retrofit standards in this country, but for the purposes of finding these killer buildings, it's very conservative. And to demonstrate that just quickly, there's a couple of databases that have been evaluated very thoroughly by very competent structural engineers, by our robust evaluation standards, and one of them is a bunch of California hospitals, and I won't bore you with all the data, but 966 out of 1196 failed this criteria. So if someone passed a concrete building ordinance using that criteria, almost all the buildings would have to be retrofitted, and it's an enormous cost, and very few people will pass such an ordinance. The California courthouses also had a very well-controlled database, and for their database of older buildings, 154 out of 210 failed our evaluation standards. And in concrete, it was a little bit worse. It was 80 out of 107, 75% failed. So the problem is simply that even though LA passed the concrete building ordinance, it remains to be seen how that's going to work. But if they use the current evaluation standards, there are many concrete buildings are going to have to be retrofit at a very high cost. So our objectives was to identify buildings that we really thought have a high probability of collapse, not just having a lot of damage, but are really could collapse. But we wanted to do this without all the sophisticated analysis that's available because it costs too much money. You can easily spend $50,000 or $70,000 of structural engineering time doing a full analysis of these buildings, and that was not desirable. If possible, we would like to we would like this methodology to give some idea of what's the possibility of global collapse, because that's really the killer building that we're trying to identify. And if possible, it would be nice to be able to rank the buildings. So you could say, I have 100 buildings, and this one is the worst, and you go all the way down to number one, and then a community could sort of say, I want to fix the bottom 20% or the bottom 10% or whatever. These are the desirable traits that we started with. One of the problems is the older concrete buildings have a huge variety. Their lateral force resisting system, which some people have talked about, many of the ones were built before the code, so they have no lateral force resisting system. Some of them have what we call moment frames, which is just beams and columns, and some of them have shear walls, which are solid walls that resist earthquake forces. All those systems, lateral systems, are then combined with gravity systems, which hold up the gravity load, and there's many, many different kinds of gravity systems. So by the time you add these two variables together, you have many, many different types of buildings, and coming up with a method to simply decide which ones are killer buildings has been difficult. But generally, the ones without walls are generally considered the most risky, so that's where this project started. So all the frames in the buildings, what you wanted to consider, both gravity and lateral force resisting frames, because it's the columns that collapse buildings, and many of the columns in buildings are simply part of the gravity system. But we have to analyze those columns to make sure, or to see whether they're going to collapse or not. They are the potential source of collapse, and we have the lateral frames and the gravity frames we have to worry about. There are different kinds. I'm not going to bore you with that. Based on a probability of column collapse, which we're calculating in the simplified method, including the uncertainty, you've heard about probabilities and uncertainties and all that kind of stuff. The story collapse mechanism is calculated. Bob Hansen gave you a lesson in probability by showing the Monte Carlo system. We use the same kind of probability by combining the probability of all the individual column collapses to try to get some idea of the probability of the entire building collapsing. That's what the method is. And we're basically coming out with a rating based upon the probability of collapse. So 1 is pretty much very bad. That's like 100% chance of collapse. And 0 is very good because that's almost no chance of collapse. And we go 0.1, 0.2 by steps of a tenth. The frame methodology was intended to have these for jurisdiction to use, and they could take the high-rated buildings and say, fix those first, and you can use it for the purpose of setting the milestone or the deadlines, or some jurisdictions might just say low-rated buildings you don't have to fix at all. It's up to a policy about how to use this methodology once it's available. The frame methodology is on the ATC website now. We finished the frame methodology and wanted to use it, so the LA Building Department came up with some money to identify some buildings in LA that we could use the methodology on, and then FEMA came up with some money, so we ended up the Los Angeles buildings, we had 7 frame buildings, and ATC, we sponsored an additional 8 buildings. So structural engineers submitted their buildings and we had them run our methodology on it. The conclusions from these tests are not complete yet. We're looking at them. But one of the conclusions is the procedure we came up with doesn't meet the simple criteria. The engineers all decided that they could use it easily enough, but it was too labor intensive and it would cost more money than was intended. That would scare away jurisdictions from passing an ordinance because the owners would say, I'm not going to do the evaluation. So we're now trying to refine it and make it a lot simpler. The final methodology, we're now working to put walls in it, which even makes it more complicated. So we've changed a little bit of our strategy. We're now trying to more quickly identify those buildings which we really think are high risk. And these are some reasons why they might be high risk. And then also come up with some easy ways to identify the low risk, which is much simpler than what we had before, and then all the ones in between might have to have a more intensive calculation procedure. But this is the methodology that we're now about 50% done with. We are covering both pure frames, that means frames without walls, and frames with walls, and also frames with masonry infill. These are all the buildings that we think that we need to cover. Now, if a jurisdiction was interested in developing an ordinance, what would they do? Well, I would recommend that you need to come up with some preliminary list of buildings that you think are older concrete buildings. I say older, but it's pre-1976 UBC. There's a lot of ways to do that. And then send out a notice to the owners of these buildings saying, please fill out this one-page questionnaire. You might have to hire a structural engineer for one day. That's cheap, because structural engineers are cheap. And please fill this out, and from that information, the city can really understand which buildings are actually older concrete buildings that should fall under the ordinance and which ones shouldn't. And they could also say, now, you people that fall under the ordinance, please run the ATC 78 procedure and submit your results. And those buildings that with a high rating could then be required to be retrofit in 5 years or 7 years. Maybe some in the middle would have a longer time, and maybe those with low ratings would never have to be retrofit at all. So we're hoping that this methodology will encourage jurisdictions to come up with ordinances, and they have not in the past simply because they know too many buildings will have to be retrofit, and they can't rationalize it because we haven't seen that many concrete buildings collapse in the country. So the purpose of this is to encourage more ordinances to fix the older concrete buildings. Thanks.
Okay, thank you. Our final speaker is Annie Cow. And Annie is a senior field engineer for Simpson Strong-Tie, where she connects and educates engineers, architects, and building officials and contractors on design and product solutions for wood, concrete, steel, and masonry in the Southwest U.S. Obviously, you've got a wide range of skills and activities. Prior to joining Simpson, she worked as a project engineer on commercial and multifamily projects for a structural engineering firm here in California. She currently serves as co-chair of the 2016 CIOSC Summit, an annual event to promote building resiliency in Southern California.
Thank you. I have to say that I was very excited to be included on such a distinguished panel. I think I work on a different end of the spectrum than most of the gentlemen here. Everyone's kind of helping to set methodologies and policies, and I work on the other end. I'm working with the contractors, the building officials, the plan checkers, the structural engineers to come up with solutions for all of these great policies that are getting put into place. So we talked a lot today, I think, about all of the great ideas that people have, and what I see in my line of work is people think it's a great idea, but sometimes they don't always want to pay for it. So one of the things that my company, as well as other manufacturing companies out there, do is try to come up with these very cost-efficient, yet still innovative solutions to help address and make practical reality solutions to actually address some of these ordinances. So I apologize, some of my fonts are showing up a little bit funny here, but I think you get the idea. So we talk about innovative and cost-effective solutions. I think we see this throughout our daily lives. So it's very possible, I think, to get the result that you want, but maybe not spend a lot of money. So for example, if you're trying not to make a mess when you're drilling a hole, a Post-it is a great tool to do that. If anyone ever shops at Costco and you get those huge plastic blister packs and can't actually get into them, you can use a can opener to try to do that. And one of my favorite, if you just have these little Lego guys around your house like I do, you can use that actually to hold some of your computer cords. So these are kind of called life hacks. Maybe you've seen them before, but really I think, innovative and cost-efficient solutions, way to use maybe technology we already have or adapt technology we already have to address some of these situations that we're seeing, such as these 46,000 unsafe buildings in Southern California. That's a lot of unsafe buildings, and we've seen a lot of examples of that here today, and especially with the city of San Francisco and the city of Los Angeles adopting their mandatory retrofit ordinances to address wood buildings and concrete buildings, such as Bill was just talking about. There has to be a way, obviously, to address these in a cost-efficient way. So we've been working a lot at Simpson, partnering with both the Structural Engineers Association and the Building Owners Management Association and the different building jurisdictions, particularly the City of Los Angeles, is how to address this specific type of vulnerable structure when it comes to wood construction, which is the soft story, right? When you have a huge open space in the first story and then the living space above. We've seen in earthquakes, obviously, that can lead to a collapse. And we saw it, we've seen it. We have that evidence from both Loma Prieta and Northridge. So how can we address this in a cost-efficient manner? So the nice thing about having had earthquakes in Southern California is that we learn a lot from them. So one huge lesson that engineers learned from the Northridge earthquake is the way that we were currently using steel beams and columns to resist earthquake loads was not working. Kind of the connection point, right? That's the critical point in a steel frame in a building, is how you're connecting the beam to the columns, is that you saw this kind of fracturing of the welds there at that beam column connection. And as Bill mentioned, you don't want the columns to fail because that's when you get the collapse. So what we do now, what structural engineers do now, is you don't want the connection to fail, so you push that failure out to the beam. And the steel beam is a really nice failure because you kind of get stretching, twisting. The beam itself is absorbing all that high earthquake energy, and you get this kind of a failure that you, whoops, I'm pushing the wrong button. Let me go back. You get this kind of a failure right here, which is a really pretty picture for engineers because you're seeing that all of that energy is basically being absorbed away from that column connection. What happens when you are dumping all of this load into beams is that you have to make sure that your steel frame stays where it's supposed to. So you have to provide sometimes these diagonal members. What happens is there are a lot of requirements when you're designing steel frames, which happens to be a really good solution for these soft story wood buildings, but it can get expensive because there are requirements to make sure that the frame performs under these high seismic areas. So one of the things that we've done at Simpson is try to find a better way, right? So as Thomas Edison may or may not have really said, there's a way to do it better, find it. So what we've done at Simpson is said, well, we know moment frames work really well for these types of buildings. We know that that's a solution that contractors and building owners are looking to, but we also know that frames are kind of a one-use kind of entity, right? A building goes through your magnitude 7 earthquake, the beam fails the way I showed you in the picture, and you kind of have to then take that element out, that lateral force element, and replace it because it's done its job. It's deformed. It's not going to be able to go through another magnitude 7 or 8 earthquake. So we thought, well, why don't you take that part of the beam that gets damaged and treat it like a fuse? What if you could remove the damage from that main structural member, put it into a fuse type element, be able to replace it, and really increase that resiliency of that building that has these elements in it? So our fuse, and we have a table down the hallway, is we call it our yield link. So basically we're able to introduce this proprietary, really cool tested element into these steel moment frames and make it a replaceable element. So this is what it looks like, all nice and marketing pictured. So what you'll see here is this is the link right here. So you have these 6 bolts that connect it to the beam, and you have a series of bolts here that connect it to the column. And what you can't see under this big plate is the yielding area. And so when that frame goes through that earthquake, that design earthquake, that link is what gets damaged, and then a contractor can actually go in afterwards, replace that link, and restore the frame to its original capacity. So when you think about being able to restore a building and occupy that building afterwards, this really opens up the possibility of extending the lifetime of that building. So this is what the frame looks like kind of in whole, but some of the innovative solutions that manufacturers are looking at with these retrofit solutions is doing things like making everything bolted, eliminating field welding. That's something else that can introduce costs on one of these job sites, is having to, have the tenants actually have to not be in the building when it's getting retrofit, because when you have welding that introduces a fire hazard, being able to eliminate some of those diagonal braces because of the special properties of that connection, and coming up with standard detailing. So just as Bill was saying, being able to design a frame very quickly in detail and install it very quickly, that's something that manufacturers are doing, is coming up with some of that standard detailing and anchorage design. So this is a new type of connection. There are new types of structural systems getting introduced that are basically outside the scope of the building code. And what happens is then that manufacturers will then pursue what's known as a code report for a product, basically a document that a third-party agency such as ICCES or IATMA UES will look at and review test data and calculations to show that it's within the spirit of the building code. So part of what we do at Simpson is not only do what's required for code reports, but we also really love testing and breaking things. And so we have a shake table, a small shake table up in our Northern California Stockton facility where we were able actually to validate the performance of this new kind of a connection. I'm trying to see if this video will play. Oh yeah, let me go back and go. Play. And this actually gives you a really good sense of, imagine that you have, your open garage down here, your living spaces above, and we are simulating some kind of mass there at the floor levels. And this is the kind of performance that you're expecting out of your seismic system, your lateral force resisting system, is that it's able to move along with your building and not collapse. So the structural fuse, as you can imagine, I'm just going to skip ahead here, does what it's supposed to. It actually stretches out, it gets damaged, it absorbs the energy, and then you can actually go in, unbolt it. And what you're seeing here is a tested link. This is the original one, so you can see it did get stretched out. We went in, replaced it, and we actually run the same test over and over again with the same beam and columns, but replace those links. So we're really lucky at Simpson in that we are able to be involved with large research projects, and we were able to do that with our strong frame in order to really validate this new idea of how to do a steel column connection. So one of the projects we were involved in was at the UCSD Engelkirk Shake Table Center, where they were looking at validating design solutions based on FEMA P807 to see for the City of San Francisco retrofit ordinance if different solutions would work. And one of the solutions that were explored was retrofitting using a Simpson strong frame. And we were really lucky back in 2009 to participate in a test at the E-Defense Center in Japan, where they have about a 40 by 60 foot shake table with the footprint of that size. And there was a whoops, I keep doing that. They had 6 stories of wood built over 1 story of those steel moment frames, and were able to validate that new technology. So the story that I really like to tell building owners when they're looking at projects just like this one is that it's possible. It's possible to retrofit these buildings in a timely manner, in an economic way. And I can say that because I've been on a lot of voluntary projects over the last few years where we've done just that, working with the contractor and the building owner. So this is a very typical City of Los Angeles soft story building. They're called dingbat buildings, where you have big open space, maybe some steel pipe columns that are set back from the front of the building. And this needed to be retrofitted. So we brought in one of our frames. It was an all bolted connection, so what you can see is that the tenants were actually still using the space as they were progressing through the project. Able to bring in the frame, bolt it together. It took about an hour to actually install this frame. And then they opened up some of the existing framing, connected the new frame back to the existing building. And this is what it looked like when it finished up. So this particular project probably took about 3 weeks from beginning of construction to end. And there are actually a lot of different solutions that manufacturers offer that can really help bring down the cost, just in terms of doing construction in new, improved ways, including using self-drilling screws instead of having to pre-drill for lag bolts, installing with screws, which really helps on retrofit situations as opposed to nails when you don't actually even have room to swing a hammer in some of these smaller places, and using post-installed anchorage when you don't have sufficient connection to your concrete. So one of the things I just wanted to point out with some of these proprietary products is that the importance really of making sure that when you're using a manufactured product that isn't in accordance with the building code is that it has been reviewed by an accredited agency and has a code report for that. And I just wanted to leave with saying, let's work together, manufacturers, building departments, building owners, all of us, to build stronger, safer structures in a low-cost way. So thank you.